Can you hear me well? And I'm not sure if you can see the slides. Okay, you can see them there. Hello, fellow data enthusiasts. I'm here today to talk about how graphs and graph neural networks can help us to improve the analytics in the healthcare domain. My name is Sonia Pipa. I'm a data science consultant for Endava, and I'm going to present you one of the most ambitious and exciting projects that I had the opportunity to work on. It's an analytics platform designed to provide the medical personnel with a tool that will help them to better care for their patients. Well, when you think about what kind of data they are using in the day-to-day business in a hospital, you might think about some medical imaging investigation or some lab results, blood tests, and stuff like that. Or maybe you think about this medical report that you are receiving when you are leaving the doctor's office. You know, that piece of paper that is sometimes printed and sometimes written by hand, specifying your symptoms, your diagnosis, maybe some prescribed treatment. Well, we are gathering all of this data into one single platform, and we try to perform a comprehensive analysis on it to give the doctor insightful information about their patients and even trying to help them to perform a better medical act by suggesting maybe some diagnosis for their patients and highlighting some anomalous data representation of the patient. Okay. This doesn't work, but on today's agenda, we will have first an overview of the architecture, then we are going to discuss a bit about why we were choosing to use the graph for this kind of analysis and how we are performing the graph data ingestion. Also, I'm going to tell you about some of the data challenges that we were facing during the development process, and also we will have a short introduction into our analytics pipelines. Now it works. Okay, this is the agenda. In the analytics pipelines and a short intro into the graph neural networks. In the end, the classical Q&A. But first things first. Our platforms allows data ingestion through various pipelines, from file transfer through directly connecting to the hospital database, if that's possible, through API calls, or even streaming data. After ingestion, this data is saved into an intermediate data storage organized as a data lake, and some of it is further processed and saved into the graph database. In our case here, it's Neo4j. This is the moment when our analytics pipeline kicks in, and we are getting data from the graph database, but also some other data from additional storage. We are analyzing it and save the results into the results database to make them available to the end customer. Our platform has a microservice architecture, which is deployed in a Kubernetes cluster. We have all of the services API exposed to an API management layer, and we have a micro front-end customer-facing solution. But let's look a bit at the analytics pipelines. So we are separating the analytics pipelines in two main categories. On one hand, we have the graph analytics, which may employ some trained models on the graph data, and we are making prediction on that, and some deterministic algorithms that help us to better understand the data that we are saving. And on the other hand, we have something that we are calling ML add-ons. These are more traditional way of applying machine learning to medical data. This means that we are analyzing medical imaging, we are classifying this type of images, and we are also extracting information from the medical documents, like those medical reports that I was mentioning before. Well, as you probably already know, when you are using machine learning models in your solution, it usually comes in two phases. First, you have the training phase, in which you are presenting the machine learning algorithm with some historical examples for your task, preferably labeled. And the models runs to make prediction based on this learned information. Right? After you finished with this training process and you are satisfied with the performance of your model, you are deploying it into let's say, the production pipeline. And we are calling this second phase the inference phase, right? So we are applying the already trained model on the live data, and we are getting live predictions on it. We are saving all of this prediction not only into the results database, but also into the data lake for future references and retraining purposes, also to assess the performance of the newer model compared with the older ones. And speaking about that, we are also versioning all of the models, and we are saving them into a model repository. And to better understand what is this data that we are working with, here is the list of it. First, we have the electronic medical records. And what are these? They are a structured format of data. We are receiving them in JSON. And they represent records of the patient created by providers for specific encounters in hospital or ambulatory environment. They usually contain information like diagnosis, symptoms, some lab results, and so on. Then we have the medical imaging, and this can refer to any medical imaging kind that you heard of it before, like CTs, MRIs, ultrasound imaging. And this data we are not saving directly into the graph database, but we are saving their interpretation, if we have it, from the doctor, or the predictions that we are making on these images. We are receiving this in various imaging formats like JPEG, but also some other specific image formats. And the last, we have the documents which represent the medical reports. They contain usually similar information as the electronic medical records, but this one is not structured. You have to extract information from there because it's a PDF or sometimes a scanned picture. But you may wonder why we are choosing graphs to deal with this data and perform analysis on it. Well, we are choosing graphs firstly because when you think about what kind of entities and interactions happen in a hospital or in the medical environment, it's a natural graph representation. You have the patient interacting with the doctor, you have the doctor prescribing something to the patient. They are both related to this hospital in which the whole thing is happening. And you may also have an entity for, let's say, every visit that you are doing to the doctor. And basically, this is what a graph is. It's a collection of nodes that are representing individuals or entities, and they may hold additional information about it. And then you have the collection of ages, which basically models interactions or relationship between these entities or individuals. And also graphs, because this helps us to save the data in a form that it's easier to query, sometimes even faster, and the result that we are receiving is more easy for the human to assess. So, for example, let's say that we want to get all the patient information. We have a doctor and we want to know some things about all of his patients. And if you have this data in a relational database, this will be translated in a query, and you have to make a couple of joins there and receive the data in this tabular format. And then you have to go row by row and assess it or investigate whatever it's of interest for you. Well, when you have it in graph, this transforms into a simple traversal. For example, a breadth traversal that is going from the doctor's node to all of the immediate neighbors, which are the patients, and then to whatever other node is linked to these patients and it's of interest. Or also another use case, let's say, for example, you want the whole historical records for one patient. You can perform the other type of traversal, which is the depth first, and you are going as deep as possible on one branch that is representing your patient from the doctor, right? And also, when the doctor is presented with these kinds of information, it's much easier for him to understand the interaction and relationship between all of these elements that adds up to create the patient's medical history. And lastly, there is one other fun thing about graphs. They can preserve the structure of the data. And I know I'm repeating myself a lot, saying that, okay, we have this relationship that are very important, but they really are. For example, we can compare graphs, and we can compare them not only by looking at the values of the properties, we can also look at the relationship between them. And here comes the graph isomorphism that helps us with this. And very short, to remind everyone what graph isomorphism is simply a bijection between one graph and another that has a very nice property saying that for any two adjacent nodes in the first graph, you'll have another two adjacent corresponding nodes in the second graph. And this can help you assess structural similarity between graphs. So let's say, for example, you want to assess the historical medical of a father and compare it with the historical medical of his son, and see if there are some similarities in there, make some conclusions based on it. Well, but how we are in fact ingesting this data that I was presenting before into the graph? First, we need a data model to represent all of those entities in the healthcare domain. So luckily, there is a standard for healthcare data exchange. It's called FIRED. It's published by HL7, and it's a regulatory standard in the US. All the clinics or medical institutions are subscribing to this standard and are using. And this simply gives us the data model. It has all the possible resources that we might have to model regarding the medical healthcare domain. And for example, if we are looking at the patient, we have some metadata about it, like an identifier, marital status, a name, but we also have those relationship modeled. So we know from this data model that the patient interacts with the practitioner, interacts with an organization, can have an episode of care, and so on. How we are transferring this into graphs? Well, we create a template graph. And this is the main tool of our ingestion process. We are taking each resources in that data model and create a root node for it. And then every metadata about that resource is going to be transformed in the metadata node. And to be more specific, let's look at this example. We have the patient, which is a root node. Then we have the relationship to the metadata node, which is the identifier, but we also have a relationship to the episode of care entity. And besides this, we also have some property nodes. These nodes are not going to be instantiated. They are only there to indicate how we are supposed to ingest the data. We have the data type for that property. We have the anchor in the data model to know exactly what information to put in for this property. And we also have some restriction if the property is required for ingestion or not. Those type of nodes are going to be saved as property labels on their parent node. So basically, this template graph is an ontology of the healthcare domain, right? It describes everything that's in there, and it helps us to instantiate it with live data about real patients. To better understand how this instantiation happens, let's focus a bit on this simplified version of the template graph. Oh, and by the way, the one that you saw before, it's not even a half of the whole data model, that big one. Fun fact. And this is just a small region of the ontology. We have the patient, and we have the practitioner, and the organization, and some other root nodes that are relevant for the patient situation. And to focus a bit on the patient node, we will see here two instances of it. And this is how the graph will look instantiated. You have here Mary and Joan that are seeing separate doctors, but they are going to the same hospital. And you see that they have, each of them, some other linked nodes that are relevant for them. It doesn't necessarily have to look the same like they are looking here. They may have different representation. But one thing that's important about this ingestion process is that we are preserving the link from the node in the ontology, in the template graph, to its instances. And why is this super helpful? Well, for querying. Because if at some point you want to get all the patients, without these links, you will have to go node by node in the graph and check, okay, is this node of type patient, then I want it. Now, if we have this node, we won't have to go through all of the nodes in the graph. We will only have to start a traversal from the root node in the template graph, following only the links that represent instantiations of that node. Moreover, this is also useful for the situation in which we want to focus our analysis on certain regions from the template graph. So we can isolate from there that we are interested in these properties, and we can simply get the instances of that region of the template graph to use it for training or for other types of analysis. Right, now the data challenges. This is very difficult, and probably everyone here, because we are all working in the data world, has faced this kind of problem before. The most difficult one is when you don't have access to actual data during the development. And you can imagine that working with healthcare data, it's even more difficult because this is very sensitive data and nobody is giving us the data to test our application in the development phase. So luckily for this, we were able to find a synthetic generator, synthetic data generator. It's called Cynthia, and it's able to generate data records for patients that contain complete medical history, including medications, allergy, medical encounters, social determinants of health, and some other. And also a fun thing about this is that we are receiving this data in a very structured format, and it also follows the FHIR standard. And this is the data that we were using during the development and to test our pipeline. The next kind of data challenges is the more difficult one. One thing is that during the ingestion, okay, we can assess some the quality of the data, putting restrictions in there, but we cannot assess, for example, if we are receiving a patient without any treatments node, right? This can mean that we have missing data, or it can mean that this patient is super healthy and never been treated. Or, for example, we can receive some blood test results, and there is a value, and there is no way for me to know at the ingestion time if this value is correct or not. It's my blood sugar, but it can be the right one or the wrong one. I need the whole context to assess this kind of information, to associate this value and interpret it in the closest context of it. And some of these cases we are treating through our analytics pipelines. Speaking of which, let's talk a bit about that. And we will start with medical imaging analytics. I know I put it the other way around. This one is from right to left. Okay, so we have trained models that are detecting pneumonia in X-rays. Our performance is quite promising. We have an F-score of 0.94. We also have a model that is detecting Alzheimer from MRIs, also with a promising score, but that's as good as the previous one, only 0.9. And more are going to follow on this category. We also have some deterministic way of analyzing the graph. For example, we are interested to identify in the deterministic matter if in our live data graph there is any patient that has invalid billing address, for example. I know this is not part of the medical arc, but it's still part of the medical world, and it's part of some of the processes that you have to do when you visit the doctor. Or another use case, we identify if a patient has been diagnosed multiple times with the same disease by different doctors in a very short period of time. This may signal some abuse of his insurance policy or even on the hospital resources, and we are flagging this. And then we are having the ML graph data analytics, the one in the title of the presentation and one probably you are expecting for. Here we are employing graph neural networks to make predictions based on the graph data. But first, some things about graph neural networks and what are they. Well, they are specific types of neural network that are designed to work directly on the graph structure. They have been successfully used before in tasks like recommendation system, for example, to recommend a friend in the social network, or even in the medical system for molecule classification. But to understand better what they are and why do we need them, let's have a look at their older and more popular cousin, the convolutional neural networks. You probably already know that this type of networks are generally used to classify images, to detect objects in the image, and these kinds of stuff. But what is an image, in fact? Isn't that like a particular case of graphs? Isn't the pixel a node in the graph that has exactly 8 neighbors? Well, it is. And what does the convolutional neural network? Well, it applies a convolution over these pixels, right? This convolution is basically a matrix with some trainable numbers in it that you are sliding over the picture, and you are trying to aggregate the values from those pixels into one future representation of your initial picture, right? And also, because you are sliding with this convolution over your initial picture, you may figure that, for example, it's important that the cat picture is in the top left corner of the picture, or it's in the bottom right corner of the picture. It might be the same cat, but it's not the same picture. And this is why the graph neural networks are very sensitive to this spatial locality. But if we want to translate this kind of behavior from convolutional to graphs, how would that happen? Well, we cannot exactly apply this convolution, this matrix, and overlapping over our graph, because in our graphs, we don't always know how many neighbors a node might have. We don't even care how close or distant the nodes are in the graph, because the only things that matter is basically the links between them, not how they are drawn. And as we saw in the first image, they can look completely different, but have, in fact, the same structure. Well, this is what graph neural networks come to solve. They accept non-Euclidean input, which are the graph, and is not structured. And they are introducing this notion of generalized convolution beyond the two-dimensional space. Right. And these are the key components and principle about graph neural networks. First, we need the input, right? We have the graph, we have the nodes that have feature in them, or they can be randomly initialized if we only care about the structure. And then we have edges that may carry weights or also additional features. And then we have the node level operations. And what are those? This simply means that in one node of the graph, you are aggregating all of the values from its neighbor by following the links. And what do you do about this aggregation when you are performing a message passing step? This means that you are updating the current value of your node with all of the values aggregating from the neighbors. You can use min pooling, max pooling, whatever kind of aggregation, even another neural network that is aggregating this information. And then you may wonder, okay, but why gather information only for my immediate neighbors? Why not from more distant one, maybe from layer 2 or 3? Well, this is the layer stacking. You can have multiple layers of aggregation depending on the size of your graph, and you can aggregate in your node information from many layers below it. So I'm getting the information from my neighbors, but my neighbors get the information from the neighbors, and so on. And then, after we have this all performed and we have a node representation for each node in our graph, we may perform graph level operations. This means that we are getting all of the nodes embeddings and aggregating them again into one imaginary node that will basically represent the graph embedding. And this helps us to perform graph level operations. Well, these kind of networks are usually trained in a supervised or semi-supervised manner. And to give you an example, for supervised, it means that you may have examples of different graphs and you have categories for them. You can train this network that these graph embeddings represent that category and apply this train model for new graphs to identify their category. Or the semi-supervised way is in the situation when you, let's say, have labels for nodes in the graph, but not for all of them, for some of them. You learn to create embeddings for these nodes that have categories. You learn to estimate the function between those embeddings and the actual labels that you have, and then you are applying this to label the nodes in the graph that you don't know anything about. And the last thing, this kind of network are usually, as any other kind of neural network, trained with using backpropagation and gradient descent for parameter updates. Right. To make this more clear, on the left side there and my right side, we have a small diagram explaining how this process of training works. And this is not so different from other training processes. You have the input, which in this specific case, there is a graph. You have the neural network, then you are obtaining some embeddings, and you have a prediction head. And this prediction head might be different depending on the task that you're trying to perform. And then you'll have the predictions, right? You are comparing that with the labels, and you are trying to optimize, basically minimize the loss function, so the difference between your predictions and the actual labels. And then after you finish the training, you can use the same method, comparing predictions with the labels, to perform the evaluation. This is the evaluation of the performance of the model. And here we have an example for node level prediction. Well, in this case, our prediction head is going to be these node embeddings that we are talking about. And we need this, for example, when we are inserting data into our live data graph for which we don't have any information about. So let's say we said that we are performing this information extraction from the medical reports, and we don't know exactly if that entity that we extracted, it's a medication, it's a different kind of treatment, it's a symptom, whatever that is. We only know that it's important for that document. We are inserted that, we link this information to the patient and other entities that are related to it, but we don't know exactly what type it is. We can use node level prediction to put a label on this kind of node to say, okay, this is a symptom. And next, we can do edge level predictions. So this means that our prediction head in this moment is going to be formed by a pair of nodes. So I'm concatenating the embeddings of two nodes, and this is basically going to describe me the link between them. And I have an encoding for that link. I can use that to predict, for example, a recommendation. I can recommend the physician based on the local context in the graph explaining the symptom, the lab results. And I can recommend that because I have learned from other examples that patients with similar symptoms and similar lab results had a good diagnosis for this specific doctor. Or another situation in which we employ the link prediction is when we are gathering disparate data. You probably encountered this in the hospital when they have multiple informatics systems. They have one in the front desk, they are making scheduling there, and they have another one, and the doctor is inputting your medical report, and there is another one downstairs when you go for medical imaging, they are giving you a CD, you go back with that, and so on. You know the story. Well, because we are getting data from all of the systems, sometimes we might end up having in the graph disparate portions of it. So we don't have the full representation of the patient medical history. And we are trying to use link predictions to connect these missing dots, right? To connect these pieces of graph and to identify that they are belonging to the same patient. And lastly, there is the graph level prediction. And here, our prediction head is basically another layer of aggregation of the embeddings of all the nodes in the graph. And this one you can use, for example, to suggest diagnosis based, again, of the graph representation of the patient system, investigations, and so on. Again, trained on historical data, another example that we are gathering. Or we are also trying to employ this kind of prediction in anomaly detection tasks. So for example, we have the graph representation of multiple patients. Let's say that some of them have the same disease and they received some specific treatment for that. And then we can identify, looking at that graph structure, that there are instances of patients that for this actual disease, they received a different treatment. And this is how we are signaling that this might be an anomaly and the doctor might want to check this out. And these are all the 3 types of prediction that we can do with the graph neural networks. Lastly, I would like to present you some of the most popular types of graph neural networks. The first one, it's from 2016, and it's called Graph Convolutional Network. This is basically the next step from the convolutional neural network, and it's a simplified form of graph convolution, in which each node aggregates information from its neighbors using the mean pooling aggregation strategy. And because this aggregation strategy is not an injective function, this type of network is not very good at distinguishing between different graph structures. Then we have the graph sage 1 year later, and this one introduces something super interesting. It's called inductive learning, and because of that, this kind of network can generalize to unseen node or to new nodes during the inference without needed retraining. So this means that if I have a graph, I learn how to generate embeddings for each of the nodes in my graph, and then I'm adding new nodes, nodes that I never seen before, nodes that weren't part of the initial structure, and I can make prediction on that. This is like a super cool stuff and performs very well for node and link level prediction stuff. And it also has this nice thing which is called the sampling strategy, in which it doesn't aggregate all of the neighbors of the node. It sets from beginning a fixed number of nodes and only aggregate those. And this significantly reduces the computational expense, and it allows you to scale to larger graph. But also the aggregation function that it's using, it's max pooling, if I'm not mistaken, also not injective, so not very good at generalizing the graph structures. The last one is called the graph isomorphism network. And this one combines node's own feature representation with the information aggregated from its neighbors. And it uses for disaggregation a multi-layer perceptron. This is another type of neural network, and transform this aggregation function into an injective one. And this allows it to better differentiate the graph structures. Well, this was my presentation, but before closing it, I would like to leave you with some question. What other domain do you think it might benefit from this kind of analysis using graphs and graph neural networks? Thank you for listening, and I think we have some time left for Q&A.
Thank you, Sonia. I do have an answer. Maybe public transportation, maybe a use case for this.
Sorry?
Maybe public transportation, maybe a use case.
Definitely, yeah.
Very cool, yeah.
Thank you, Sonia. It was very interesting. At least for me, it was one of the best presentations I've seen today. So
I'm glad you like it.
Yeah, maybe cybersecurity can be another domain, but I have a question related to the domain. How much healthcare knowledge or domain knowledge need a data scientist to actually build a healthcare genome?
Well, you do need some knowledge, but basically, I didn't know anything before starting working on this. But it definitely helps to have a bit of knowledge in this area. But usually, if you are provided with enough data examples, you can identify the use cases just through the data science mind, that by looking at the examples and knowing what these tools are capable of. But definitely, it helps a lot discussing with the doctors and involving them in the process and asking them what, in fact, are their problems, not something that I imagine I can solve, and it will be useful for them.
Thank you.
Thank you for the question.